All right, here we go. So just to sort of recap what we've been doing, okay? Up till this point, guys, we have covered how to handle a calculation involving a strong acid, strong base, weak acid, weak base, and we also looked at how to do what's called a percent dissociation calculation, which is exactly the same setup. It's an ice table, the whole thing. It's just a little bit different at the end, okay? We are going to wrap up our section on acids. We finished on bases last class. We're gonna go back to acids for just a little bit, and then we are going to completely change gears for the last part of the chapter. Please remind me, we've seen this word before. What does polyprotic mean? Many what? Protics. No, wrong. Protons, okay? It means, more specifically, an acid that can donate, because remember, that's the definition of an acid, something that can donate a hydrogen ion. These are acids that can give away not just one, but 2 or 3. And here's an example. Okay, this is carbonic acid. And the first thing that I want you to realize is that if you have, like this example, an acid that has 2 hydrogens to give away, I need you to understand that those hydrogens do not come off at the same time. Okay? These 2 hydrogens are not donated in one shot. Okay? They are donated one at a time. So there's 2 separate reactions here. If this were a triprotic acid, meaning something that has 3 hydrogens to donate, you would see 3 dissociations. Okay? So that's really important, first off, is that these hydrogens do not come off all in one shot. They're removed one at a time. Yes, sir?
Are there conjugate-based problems with these acids?
What do you mean a conjugate base?
Where it'll ask us which conjugate base?
Sure.
So would it be...
So if this is the acid, that's the conjugate base.
Okay, even though we can still punish by the proton.
Correct. Now, in this reaction, just this one, this is the conjugate base. If you're looking at this one, this would now be classified as the acid, and that's the conjugate base. Okay? Do you all remember the word? It was a vocabulary word, something that can act as an acid or a base. Amphoteric. Can you tell me what compound on this slide is amphoteric? HCO3 minus. Okay? This guy can give away a hydrogen. It can also accept a hydrogen. Okay? Now, I want you to also notice that these have their own Ka values. Okay? Carbonic acid has a Ka value, and this ion has a different Ka value. That's why it says Ka1, Ka2. All right? Now, here's the good news. Okay? When you're dealing with a polyprotic acid, all right, let's go the extreme. Let's think of an acid that is triprotic, has 3 hydrogens to give away. In theory, okay, let me give you an example. Let's say we were given this acid, phosphoric acid. Strong or weak? Weak. How do you solve for the pH of a weak acid problem? What do you have to do? Everybody. An ice table. Well, if each hydrogen comes off one at a time, that would be 3 separate ice tables all in one problem. Yikes. Here's the good news. Are you ready? In calculations, we can normally ignore the second, and sometimes if there is a third, like that one, dissociation, because the first is so much larger. Okay, now let me break that down for you. Okay, remember, 99% of the time we're being asked to calculate a pH. What do you need ultimately to calculate pH? Concentration of what? Hydrogen ions, okay? Do you agree that this first reaction is producing hydrogen ions? How about the second one? Okay, they both are. Here's the point though in this statement. Is this second or even third dissociation, is it producing H pluses? Yes. But these second or third dissociations are producing so few H plus ions that when you round the pH to significant figures, the pH is not going to change. Once you've calculated it after the first dissociation, if you calculated it after the second and third, it wouldn't change. So, do you need to worry about them? No, you don't. Okay? Now, would you have to do an ice table for the first dissociation? Yes, you would. So, let's just look at an example. Okay? I'll get to that in a second. This gets into a little bit of something that we have not yet talked about, but it's going to be big time in chapter 15. Do you know what the word titration means? Adding what to what? Acid to base. Okay? We have not done any calculations yet where we had an acid and a base in the same problem. We've done calculations where we had just 1 weak acid or 1 weak base. Chapter 15 is all about combining acids and bases into the same problem. And if you do that, we're going to look at something, some graphs called titration curves. Okay? I'm not going to get into the details of this. All I want you to recognize here is that a monoprotic acid, meaning just one hydrogen, when you are doing a titration, has this characteristic S-shaped curve. I just want you to notice the graph on the right, a diprotic acid, something that has 2 hydrogens to give. Can you see that there are 2 S's? And if it was a triprotic acid, let me do my best here to draw this out. It would be 1, 2. All right, it would look something like that. Okay? Basically, the number of S shapes that you see is an indication of how many hydrogens there are to be donated. Okay. Now, let's do a polyprotic example. It says, calculate the pH of a solution of 1 molar arsenic acid. Okay? First things first, before you do any problem in chapter 14 or 15, strong or weak? Weak. Okay? Anything weak is going to need what to solve it? An ice table. Okay. Here is what I want you to do, and you're going to do this on your own. I want you to write the reaction for arsenic acid in its first dissociation. Remember, all 3 hydrogens do not come off at the same time. Write the reaction for its first dissociation, set up your ice table, solve for pH, and stop there. Go. What do you think I'm going to ask you? Does it? How do you know? Because it's an acid. Okay? Remember, I keep saying this over and over again because I keep hearing people ask about it. Do not worry, where is it below 7? Okay? Just, is it in the acidic range? Yes, good, move on. Okay, now, this was a triprotic acid, okay? And the question, or the 2 slides back said we don't need to worry about the second and third dissociation. But ladies and gentlemen, I want to very quickly prove it to you. So what I'm going to write next, it's your choice. You can either write it down or you can just watch. Can you tell me, for the second dissociation, what would be my acid on the reactant side? Thank you very much. What would be the conjugate base? Okay.
-2.
Very good. Okay. I'm going to do this very quickly. Okay. Now, just for your information, because I think this is actually very cool, these dissociations happen one at a time, meaning this second one will not happen until the first one is over. So what's initial here is what's final above it. So, tell me this. At the end of the first dissociation, so on this E level, was there any of this at the end of the first dissociation? Okay? And what would the number be? X, which we found to be 0.068. Still don't care about water. How about this guy? No, wasn't even in the equation, so that's 0. How about this guy? Plus X, plus X. What am I setting this equal to? Ka2. And ladies and gentlemen, please notice that this expression is not going to look like they always do. And that's a good thing, because starting very soon, our equilibrium expressions are not always going to be x squared anymore. So this is a good little sneak preview of things to come. Now, I'm not going to ask you to graph it. I'm going to tell you what x comes out to be, and this is not a coincidence what x comes out to be. Don't ask me to explain it mathematically. Essentially, what's in the parentheses cancels out. Okay? Now, tell me one more time. If I'm trying to find a pH, what is the one thing that I need to find in order to do that? The concentration of H+. Okay, great. H+, H3O+ are the same thing, yes?
Yes.
Okay, here it is. If you would, please, put in your calculator 0.0683 plus 8 times 10 to the negative 8. Do it. I'm doing it too. Oh, you're doing it. .06830008. Yes? Okay. How do you turn that into a pH? Okay. Negative log of that answer we just found. Tell me what the pH comes out to be. 1.1 7. Okay? Ladies and gentlemen, it's not enough that you just watch me do this calculation. Are you going to have to do this? Probably not. But I need you to understand conceptually why our final pH down here was exactly the same as the one above it. Did this reaction actually occur? Yes. But based upon how small that Ka value is, that is telling me that this reaction, although yes it does happen, does not go in the forward direction very much at all. So I'm not getting very much more of this than I had above it. So the pH is not really going to change. Ladies and gentlemen, we are completely changing gears now.
Oh, goodness.
We are leaving the land of acids and bases. We are entering the land of salts. What's a salt? Don't say NaCl.
One anion.
Okay, thank you. Very good. Any ionic compound is a salt. Okay? And that is what I mean from now on. When I say a salt, I mean metal, non-metal, cation, anion. Okay. Well, guys, you may not realize this, but when you dissolve a salt in water, the pH is affected. Okay? You probably don't think about that. You probably don't think about the fact of, like, when you're drinking, you dissolve, powdered lemonade in water, or like fruit punch or Kool-Aid or something. You probably don't think about the fact that when you just simply dissolve something in water, that the pH can change. You could make it into an acidic solution. You could make it into a basic solution. Okay? Here's what you will be expected to do. Not necessarily at the end of today, but certainly by the end of Thursday's class. I can give you any salt, any ionic compound I want, and just by looking at it, no calculations, just looking at it, you will be able to tell me if that salt is dissolved in water, it's going to make the pH go below 7, above 7, or stay at 7, just by looking at it. Okay? So, here is the thought process. Okay? I said something at the beginning of this chapter that I didn't really follow up on immediately after, and now I am. Somewhere, many slides back, it says to always list your major species. Well, guys, this is, from now on, going to be something essential that you do. Ladies and gentlemen, water is always one of your major species. Always. Let's look at this example right here, sodium chloride. Can you please tell me, if I put sodium chloride into water, what happens to it? Okay? Chemically, what does it mean for something to dissolve? Dissociate, ionize. Okay? So I'm going to have a bunch of Na pluses and Cl minuses floating around. This example has 3 major species floating around. Okay? Well, let's think about, and this is the thought process you're going to need to do, really from now until the end of chapter 15. You need to look at your major species and think about what are the possible reactions that could occur. Let's start with the Na plus ion. That ion could react with water, and I'm going to write water not as H2O, but HOH. You don't have to. I prefer to, and I'll explain why, but you certainly don't have to. I like to think of water as an H plus and an OH minus put together, because that's basically what it is. Can you tell me which part of that HOH could possibly link up with something like Na plus 1? Okay, why wouldn't Na plus and H plus go together? Yeah, you don't put 2 positives together. Like charges repel. Okay. So you're right. Here's one of my possible products, which would leave me with what as the other product? H plus. Okay. All right. This is a possible reaction that could occur. Tell me this. Acid or base? Base. Strong or weak? Strong. Okay. What does it mean for any acid or base to be strong? Completely dissociates. Okay. Let me say that another way. If you say that something completely dissociates, does that mean that this is a compound that likes to be together or likes to be apart? Apart. Look what we're doing. We're putting it together. Does it like to do that? No. NaOH, ladies and gentlemen, does not form. It doesn't form. It dissociates. So guess what? This reaction is not going to happen. And it's not going to happen because one of your products is a strong base. Strong bases don't form. They break. So that's not going to happen. So the Na plus is not going to react. I'm going to cross it off. It's not going to happen. The Cl minus might. Let's try this one. Can you please tell me what part of the water here might this Cl minus link up with? Okay. HCl. Strong acid? What does that mean? Completely dissociates. Does not form. This is also not going to happen. If these two things are not going to react at all, guess what the pH is? 7. No part of that salt is going to react. That salt will dissolve, but ladies and gentlemen, dissolving is not a chemical process. That's a physical process. This is an example of what we call a neutral salt, meaning you dissolve it in water and the pH is going to stay right at 7. Now, not all salts do that. Some salts are what we call acidic salts. Some are basic salts. That's a neutral salt. Okay? Now, remember I said that you would be able to just look at a compound and without doing any math or anything, just look at it and figure out, is that a neutral salt? Well, this is the long thought process. This is the chemical reason why the pH stays at 7. But let's look at another example and I'll show you kind of the shortcut way to think of this. First of all, I personally find it very helpful to draw a line in the salt that separates the cation and the anion. You don't have to do that. I just find it helpful. Okay? Here's the deal. With any salt, cations, the first element listed, will always form some kind of potential base. What base could this possibly form? KOH. Strong or weak? Okay? I'm going to put a little S for strong above that side. Anions always form potential acids. Anion acid, AA. What acid could this possibly form? HNO3, strong or weak? Okay, I'm going to put another S for strong. Are either one of those reactions going to happen? No. Guys, when you have a strong combination like that, that is a neutral salt. You could have a question like, which of the following salts is a neutral salt? Blah, 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 blah. Okay? You are looking for the one that has the strong combination. But what if it's not a strong combination? For example, sodium fluoride. Okay? Here are my major species. All right? Okay, let's go through the thought process again. Cations, the first element in the compound. Form bases, NaOH, strong or weak. Okay, I'm going to put a little S above it. F minus could possibly form what acid? HF, which is weak. So right off the bat, ladies and gentlemen, this is not a neutral salt. Okay? This guy is not going to react. But this guy will. Can you tell me what my products would be here? Okay, HF and OH minus. Okay, now let's just break this down. Hold on. Why is this going to happen? Why is this a reaction that will occur? What's weak? Okay, what does it mean to be a weak acid? Doesn't dissociate. Let me put that in other words for you. Likes to be together. Likes to form. And guys, look at what the other product is. If you're completing a reaction where you're making lots and lots and lots and lots and lots of this, what do you think? Where do you think the pH is going to fall? In the basic range. So this is an example of a salt that if I was dissolving it and monitoring the pH the whole time, we would see the pH start to climb above 7 as it dissolves more and more. Okay? Now, what do you think I'm going to put underneath this? An ice table. Oh-ho! Okay. Well, this is not an example problem. I'm not given any numbers, but let me just illustrate something for you here. So I would have some kind of initial molarity, blah, blah, blah. 0, 0. It's going to look a lot like we've seen before. Plus X, blah, 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 minus X, X. There's a little catch here, though. Okay, A equals X squared over blah, 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 minus X. Okay, fine. Notice I did not write a letter here. I mean, I'm going to eventually. Do I need a Ka or a Kb? Are you guessing? You're guessing.
C. It's B.
Okay. How do you know? I mean, up till this point, you haven't really had to think about this because it was just the one that was given to you. From now on, you're going to have to think about it. How do you figure it out? Let me show you. This is the reactant you need to be looking at. In case you haven't noticed, every equation we have written so far this entire chapter has been something plus water, right? The something determines what letter we put here. What is this something doing from left to right? What is it doing? Is it giving away a hydrogen or accepting one? Okay. Something that is accepting a hydrogen is by definition a base. So I need a Kb. Here's the catch. That wasn't the catch. This is the catch. I'm not going to give you that Kb, nor is the AP exam, because we're just jerks. What are we going to give you? We're going to give you this. Well, that's helpful, because that's not what I need at all. Okay? I'm going to give you the Ka for HF, which is not what you need at all. Not to panic, ladies and gentlemen. there is an equation on your equation sheet that looks like this. Intriguing. You have a number for this. Anybody remember what it is?
1 times 10 is
Negative
14.
14th. You were close.
I had half of it.
Okay. This is 1 times 10 to the negative 14th. I've given you this one.
Bye.
Can't you find this one?
Yes, you can.
But guys, listen, before we do an example problem, the point is, the take-home message here is, you can't rely on the value given to you in the problem. You have to be able to look at your reaction and say, well, which one do I need? Do I need a Ka or do I need a Kb? You have to figure it out, because we're going to try to trick you, because we're jerks. Yeah, that's true. So let's do an example problem. Here we go. Okay, if you want the mathematical proof for why this is true, go see the proof in the book. Okay. Ladies and gentlemen, here is our salt. Sodium azide. Azide is an ion that you are probably not familiar with. This is not sodium nitride, by the way. That would have a formula of this. Okay? Sodium azide. I draw a line. Okay? Here are my major species. Na+. This is what the azide ion looks like. And water. It says sodium azide is sometimes added to water to kill bacteria. This is also, by the way, just out of curiosity, the starting reactant for an airbag reaction. Sodium azide. Okay? This is what provides the nitrogen gas that inflates an airbag. Okay?
Is it that mild? Is that quick?
Yes, it is actually. It is very, very quick.
You were talking about this last time.
Yes, we will. All right, it says calculate the concentration of all species in a 0.01 molar solution of sodium azide, and then you're given some other information. Can you please tell me what kind of combination is this salt? Is it a strong, 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 weak, weak, strong, strong, weak? Which one of these ions is the one that will react? Okay. As strange as it is to say it, it's the weak side. The weak ion is the one that will react. All right, so here we go. What's one of my products here? Yeah, here's a little clue right there. But yes, you're right. Because the anion always forms some kind of acid. What's my other product? Okay. Now, ladies and gentlemen, I cannot stress enough. Before you do any math, I know the question set doesn't say to calculate a pH, but we're going to do that anyway. Before you have done anything, you should be able to tell me where the pH is going to end up. Acidic, neutral, or basic? It's going to end up basic. So right off the bat, you should be able to know, you'll have something that's going to help you decide whether your answer makes sense or not. Okay? So, let's set up our ice table. All right. We were given a molarity for this entire salt. Salts split, don't they? They split up, they dissociate, yes? Okay, so guess what? This ion is also going to have this molarity. Because there is one azide ion within this one compound, they'll have the same molarity. Anything to put here for a starting molarity? Okay, hold on, Reed. And this one? Okay. Yes, Reed.
This one had two azide or two will be
Yes, it would. It would be 0.02. Very good. Okay, minus x plus x plus x. Please tell me what kind of K I want here.
KBE.
Okay. Refresh my memory. How do you figure that out? Look at what. Don't base it on what's given to you. You look at what is given, what your reactant is doing. It's accepting a hydrogen. This is a base. How do you get a Kb from this number? Kw divided by Ka. Very good. So Kw divided by Ka will give me the Kb that I need. Okay, now solve for x.
Without one.
Okay,
2.29 times 10 to the negative 6.
good. That's what I got as well. Okay. Now, the question said, what is the concentration of all remaining species? That means anything left at the end. How do I find it for the azide ion? Yeah, plug X back in. And actually, when you end up rounding for significant figures, it's going to end up being the same molarity. And these other two, right, are equal to each other and are just what we found for X. I want you to go one further step, even though it's not printed on the slide. Give me a pH. Sounds right. Does it?
Yes.
It's a basic salt, which we knew from the very beginning because this was one of my products. Okay? Yeah, use this to find the POH first. Subtract it from 14. Okay? Now guys, I will tell you, as much as I have said, don't worry about where this falls in the basic range, I do want you to be aware, when we say that a salt is basic, okay, that's true, but a basic salt is never going to give you a pH as high as a weak base or a strong base, okay? pHs for salts, guys, are going to be much, much closer to 7 than, say, weak bases or strong bases, weak acids, strong acids, okay?
So just make sure it's relatively consistent.
Correct. Well, even, yeah, yes. And honestly, if it's in the right range, you're good. I just wanted you to be aware that your pHs for salts are not going to be like 13.9. No, the concentration of Na plus would just be 0.01. It's a spectator ion. Nothing happens to it. So that is where I'm stopping today.